With today's lecture, we're going to be looking at evidence, specifically evidence for evolution, over long spans of geologic time. The associated reading for this lecture in the textbook is Chapter 11, specifically Section 3, and in Appendix B of the textbook there are some nice diagrams of the eras and periods of geologic time. The Earth is very old. We're going to talk about the various stretches of time in Earth's history today. So I want to open with what we call the 24-hour clock analogy. To break this down, we're basically taking the entire span of Earth's history and we're setting it relative to a 24-hour period, as if it were all crammed into a 24-hour day. What that means is that at hour zero, that is analogous to the formation of the Earth, which we estimate at about 4.5 billion years ago. And then, following this 24-hour analogy, it's not until about 4 a.m. that we actually get the first origins of life, that we see the first evidence for the beginnings of living things and organisms. Progressing through Earth's history, through this day, it's not until about 2 p.m., so over half of Earth's entire history do we start getting single-celled algae, so the first time that we're actually having organisms do photosynthesis. 3/4 of the way through Earth's history, so at 6 p.m., do we actually get sexual reproduction instead of just asexual reproduction or cloning. And then it's once we start approaching the end of this 24-hour period that we start getting this diversity of animals, of animal forms happening in a relatively rapidly amount of time. And the evolution of humans doesn't happen until 11 p.m. and 58 minutes, very, very close to midnight. So the evolution of humans happens at 1 minute and 17 seconds before midnight. We've only been around, based on the history of the Earth, for a very, very short amount of time. How are we getting these oldest dates? We've been able to estimate the age of the Earth through a process called radiometric dating. Radiometric dating is the process of comparing relative amounts of isotopes in a sample to determine the age of the sample based on the half-life of those isotopes. Radioisotopes are unstable forms of elements that decay into more stable forms at a constant rate over time. And we know the rate at which certain isotopes decay into other isotopes. That rate is called half-life, and it's different depending on what isotope you're looking at. So by looking at the relative amounts of each isotope in a sample of Earth, we can tell how long it's been in its current form on our planet. For estimating very old objects, like the age of the Earth, we can use isotopes like uranium-235, because it has a very long half-life. We find this isotope in minerals like this zircon. The one pictured here is one of the oldest samples known that was found in Australia. Uranium-235 has a half-life of 704 million years. So what that means is that over the course of 704 million years, a sample with uranium in it will have half of the original uranium turn into lead in that amount of time. Uranium is radioactive, and that means it loses atomic particles over time, and in doing so it decays into a different element with fewer protons, neutrons, and electrons. If we picked up a sample and compared these two isotopes, uranium-235 and lead-207, what it decays into, and we saw that our sample was 12.5% uranium compared to 87.5% lead, we could figure out the age. That would be something entirely made out of uranium being cut in half once, that amount in half again, and then half of that. So 3 halves is 3 half-lives. It took the duration of 3 half-lives to reach that amount. So it would be this amount times 3, 2.1 billion years old. That's how we figure it out. The application of isotope studies to geology brought the current estimate of Earth's age to approximately 4.54 billion years. This is the age of the oldest samples we've been able to find on Earth, which means that the Earth may be even older. 4.54 billion is a minimum age. If instead of the clock analogy, we just use a simple timeline, we can compare how long different kinds of life have been influenced. Look at them like this. We see that there's a progression of landmarks in life forms, that the developments that come later on in this timeline are based on the advancements that develop and evolve in the ones that predate them. So, very early on, we see the first evidence of water. There's evidence that there was not always water on the planet very, very early in Earth's history. Some of the oldest stone that we found on the planet, about 4.3 billion years old, from northern Canada, doesn't show the characteristic signs present that are there when water is present, or erosion, for example. We get the first evidence of single-celled life around 4 billion years ago, and then the advent of photosynthesis, followed by the evolution of eukaryotes, so everything up until then was just prokaryotic life forms. For a very long time, there are just single-celled prokaryotes and eukaryotes, and then we get the advent of multicellular life, followed by sexual reproduction, and then very quickly, just like with that clock analogy, a very expansive diversification of life sort of crunched up into the end. Why talk about the history of Earth? It seems like a topic for geology. We do it because it relates to how life has been shaped over immense spans of time. The climate and geology of our planet have changed over hundreds of millions of years, and that has caused dramatic changes in the life forms on Earth. In the time since Earth was formed, what we call geologic time, both the land and the climate have gone through massive changes over and over again, constantly being reshaped. Geologic time provides sufficient time for the process of natural selection to create large-scale changes in organisms. We just talked about the mechanisms of evolution, and because it happens across generations, it takes a long time for there to be small changes, and an even longer amount of time for there to be large-scale changes. But luckily, there's been hundreds of millions of years of evolution happening with constantly changing selective pressures that pushes life into new shapes and new forms. Consistent long-term change in the Earth is what has steadily pushed life to diversify. If the Earth was static and unchanging, life would evolve to be well suited to it, to where it lived, and then any change in the species would slow down or stop. But an ever-changing world provides ever-changing selective pressures, pushing populations to have different phenotypes back and forth. At a certain point, only cold-adapted things survive. Okay, now only warm-adapted things survive. Big floods, now you have to be well-suited to aquatic life. When we've had millions of generations of life all subjected to different environments, it generates diversity of forms. So now we have a lot of species of organisms. There are about 1.5 million species that we have formally described, and millions more that await discovery. There are over 17,000 species of ants alone. That's just ants. Projections based on the rate at which we discover and find new species, we think that this 1.5 million is only like 15% of current species. Our current estimates are that there are 8.7 million species on Earth. However, as fast as we're discovering species, we're losing many more. It's very likely that many species on this planet have gone extinct in the last century before they were even discovered. Present-day species, the ones that are existing right now, constitute less than 1% of all the species that have ever lived on the planet, because so many life forms have become extinct. That's crazy. If you think about every single kind of living thing that currently exists, that you can imagine, that's just 1% or less than 1% of every kind of organism that lived on the planet ever. there have been so many more kinds of life, so many more species present on this earth than are just here present today. And we know this from the fossil record. We know about previous forms of life on this planet because of fossils. Fossils provide us with evidence of a few different things. They provide us with evidence that past organisms were unlike organisms alive today, in some cases. They provide evidence that many forms have disappeared from the Earth completely. And they provide evidence that life has evolved through time by looking at certain similarities in fossils with the things that are alive today. What fossils are the preserved remains or impressions of individual organisms that lived in the past, and they're often found in sedimentary rock. The word fossil has a lot of definitions, but I like to think of a fossil as any preserved piece of evidence of a living thing. A fossil can include old organic tissue, but is most commonly calcified remains. It's stone left in the shape of a living thing. Fossils form when hard parts of animals like bones, teeth, and shells are preserved in sediments, and over time the sediments harden into rock, and the minerals replace the organic materials. So different kinds of stone basically replace the elements that formed the organic material. Fossils can also be formed by other means, such as when insects are trapped in amber, which is hardened tree sap, or just the image of a fish compressed between layers of sedimentary rock. A fossil can even be a footprint that's filled in with mud and has hardened to stone. Although fossil preservation is actually a rare event, particularly for organisms that have few hard parts or ones that don't live near areas where sediments form, fossils are an invaluable resource for glimpsing the history of life on Earth. The older fossils are found in deeper, older rock layers, and because of that, the order in which organisms appear in the fossil record provides us strong support for evolution, right? This idea or this notion was the thing that Georges Cuvier was basically first seeing and discovering. We talked about that.